All right, well, welcome to Group 15's Critical Design Review, CDR. Our project's name is SecureScape. All right, and so a little bit of an introduction to the group and our project. SecureScape is a smart portable security system designed to detect motion, classify threats, and then provide alerts in remote areas where you don't have access to the internet or Wi-Fi. And so I myself am Jackson Topol on the left here, and then we have Colin Kirby, Philip Morano, and Dylan Myers, and we are two computer engineers and two electrical engineers.
Our group came up with this idea because there is a lack of security options for outdoor activities without cell service. Our goal is to create a security system that is completely off the grid without losing any functionality of a standard security system. We will achieve this goal through two types of devices, namely our node and our gadget. Later in the presentation, we will describe and illustrate each part's functionality. We want to be able to let the user know more than what a basic sensor can do. With time permitting, we will have an advanced algorithm that distinguishes the identity of the approaching suspect. Our alarm system is triggered automatically, but we also want the user to have more control over every peripheral and every piece of hardware.
For specifications, our three demonstrable specifications are detection accuracy, response time, and detection range. This should give us a good baseline of functionality.
Our next section will be about hardware. I will begin with the selection process, followed by Dylan, who will provide an in-depth look into our PCB design. The breakdown of our project includes 4 devices, a central gadget for the user to interface with, and 3 nodes that will give 100% coverage of an enclosed area. Each node will have 2 ESP32 cams for better coverage. There will be a router attached to the gadget for the nodes to speak to the gadget over Wi-Fi. Our goal is to get a single node talking to the gadget, and we will expand if time permits. In order to stay within our self-restricted budget, we decided to choose the ESP32 cam. It is not the strongest MCU level camera, but is a solid option for its price and overall better for our project than other types of cameras. Our group will be using 2 types of LEDs. The nodes will have a piece of cob strip wrapped around the housing to provide the user light functionality for their surroundings. We chose through-hole over surface mount because of their large size and ability to stick out of the gadget's housing. Piezo buzzers will be used in our system's alarm state. They are much smaller than portable speakers and nearly as loud. The buzzer will produce a slightly quieter sound due to not meeting the rated voltage, but still meets our expectations. Please excuse the contrasting colors. They will not represent the final product. This is a legacy CAD design of the nodes. There will be extra space on the underside for PVC pipes to be installed. The slanted edges of the green cutout will have ESP32 cameras attached on both sides. The gray bar will be able to hold down the green section and also be removed for easy access to the MCUs. Our gadget's MCU will be the ESP32S3. We chose the ESP architecture based on familiarity and its low cost. We found the S3 to be the most powerful version available. Low dropout regulators are easy to implement and design around. Our fixed 3.3 volt LDO is a great fit for both the node and the gadget. The operating voltage range is wide enough for easy testing and is cost effective for the output that our design requires. It is important for our system to have memory for image processing data. We chose to use the microSD for its small dimensions and low cost. We will use the GL iNet router with the model name Shadow. The device only weighs 1.4 ounces and is very powerful despite its small size. It is a great fit for our gadget because the trade-off for higher speeds is not worth the dimensional costs. This block will be the housing for the gadget. Inside we are planning to include the router, PCB, and batteries. There are small stanchions in the PCB section for ease of access. There are also 2 small holes on both sides for the router's antennas.
Jumping into our schematic overview, our first schematic is the gadget. Our processor is the ESP32S3. We have a few different paths for data. We also have a 3-volt and a 5-volt regulator, as well as a built-in test functionality. We chose the ESP32 for a few different reasons. The USB native communications, as well as the built-in Wi-Fi antenna, oscillator, RAM, and flash, as well as the universal GPIOs, made it very uh, easy to implement, as well as it had all the functionality we needed. For our power regulation, we went just with a very standard linear voltage and a fixed buck converters, mostly due to the fact that they are pretty rugged and aren't very finicky. We also added a couple of functional buttons required for the ESP32. Both are pulled high. We chose the USB-C as our main power and data connections. With ESP32's S3 native connection to USB, we were able to direct connect. We've also added in a micro SD connector to host the data and the website for our system. And for redundancy purposes, we've also added in a Ethernet port to give us a backup connection to our wireless LAN if needed. Also, for redundancy, we added 8 megabytes of flash as an external in case there's any need for an onboard memory. For our peripherals and testing, we've added in 4 plugs that will connect to 4 switches on our housing. This will give us the opportunity to switch between different modes in our system, as well as built-in LEDs that will let us test these modes. Our second schematic is for our node. It's a little bit more bare bones than the gadget due to it connecting to a ESP32 CAM dev board. It basically just has power distribution, a USB connector, and a few plugs for our different sensors. Because we're also using the ESP32 as our central component for the node, we were able to duplicate a good number of the subsystems, mainly the power distributions, the USB-C, and the functional buttons. Because the ESP32 CAM doesn't function on a ESP32 S3, we need to implement a USB to UART bridge for our data connection. During initial testing, we found that the ESP32 CAM was a little bit more fragile than we were originally led to believe. This pushed us to install headers for quick removal and replacement of the CAM boards. In the node, our plugs are going to be connected to our alarm system and our sensors. And with the limited GPIO pins, we were only able to put 2 test LEDs onto the node. Moving on to PCB layout and design, we went with the same kind of design for both our boards. We chose a 4-layer design, top layer being important signals, first inner layer being ground, second inner layer being power, the bottom layer being other signals. For the top layer, our main design drivers were that data signals were as short as possible, as well as paired correctly, that all buttons and connectors were accessible, and that all components were relatively spaced apart to make them repairable or switched out if needed. For our first inner layer, we chose to do a solid ground layer to insulate the main connections, really to reduce EMI for the whole board. It made design a lot simpler, and it really gave a good low ground impedance for the board overall. For our second inner layer, we chose to make it a power layer. With the shortened power paths, we were able to limit voltage drop. It also helped with EMI reduction and design simplicity, as well as better thermal management. For the bottom layer, we chose to pick any really non-essential signals, anything that was non-data and digital really came down to this bottom layer. It really helped with design simplicity.
All right, so here we are going to be going into the comparison and selection of software. I myself, Jackson Topol, and Colin Kirby are the two engineers in charge of everything related to software, whether it's embedded software, image processing algorithms, or the front end. So for the programming languages comparison, we really looked at 4 different types of languages seen in the table on the right, and that is C/C++, Python, Arduino C++, and JavaScript. We ended up using Python and Arduino C++ for many reasons we'll get into on the next slide, but we didn't use C/C++ just because it was very complex in the fact that we couldn't really use it that well with Arduino IDE, and JavaScript it was too slow for execution for our board. So for the selection of our programming language, again, we chose Arduino C++ and then Python. For Python, we used it mainly for testing certain hardware peripherals, such as the passive iris sensor and the camera, just to make sure we were able to capture images properly and it was a clean image. And then we also used Python for communication network testing to make sure that we were properly sending stuff to web servers. And then Arduino C++ we used for all the development that's going to go and live on the boards for the ESP32-CAM and then the ESP32-S3. The reason we chose this language just because it was very compatible with the IDE that we were using, but it also offered a lot of libraries and control and efficient management over our memory. For the image processing library comparisons, again, we really did research into 4 different types of libraries that we wanted to use, which is OpenCV, TensorFlow Lite, YOLO V5, and ESP-Who. We ended up choosing TensorFlow Lite just because it was very good with what we were wanting to do, but we didn't use OpenCV just because it was had a very high memory usage, and same thing with YOLO V5. Our board is very memory and power restrained and constricted, and so we really had to be very articulate and careful with what we chose. And then we didn't use ESP-Who, although it was very compatible with ESP32. It wasn't very good for the algorithm that we were trying to create. It's mainly better for face detection. So for the main reason that we chose TensorFlow Lite as our image processing library selection, there were a couple different ones, such as the extensive resources and the low power and memory usage. The extensive resources through the wealth of libraries that are open source and free to anyone that wants to use it, and Arduino IDE made it very easy to integrate into our system, as well as the low power and memory usage is very critical to our board specifically, just because ESP32-CAM, where we are using the image processing algorithm, is a very low power board. The integration was very easy with everything, and then Edge Impulse was something that we used to help build our algorithm. So pretty much we just had to acquire our own data using the camera. We wrote a script that captured images and stored them in a file, and then we would upload them to Edge Impulse, where we could then create the algorithm using that. For the comparison of communication protocols, there's really only 2 that we researched into, which was HTTP and WebSockets, and simply just because we didn't need anything more complex than that. We ended up choosing HTTP just because it was very compatible with ESP32, and it allowed us to easily use open source functions, making it very easy to send messages back and forth through our router. For the selection of a communication protocol, we ended up choosing HTTP. We chose this because it was very simple to program and develop, and it was very compatible with ESP32 libraries, meaning that there were a lot of HTTP libraries open source made available to anyone developing in the Arduino IDE. And another reason that we chose this was because it had very low resource consumption, which again aligned with our goals for the board, because they're both very low power and low memory. And integration was very easy. It allowed a reliable communication between the nodes and the gadget and the mobile app.
In our research to discover the framework we wanted to use for our mobile app, we compared Flutter, React Native, Ionic, and Xamarin. The table on the right compares some of the most important aspects we decided for our framework. Our selection for the mobile app framework is Flutter. Considering its near-native performance, which is very important for image processing, its very customizable UI, and the ability for cross-platform support for development with iOS and Android made it a very easy choice for us. In our research in deciding how we're going to host the mobile app, we evaluated AWS Lambda, Firebase, Heroku, and DigitalOcean. The table on the right compares some of the most important aspects that defined our decision, including performance, scalability, cost, and ease of use. In our final decision on where we would host the mobile app, we considered the requirements of responsiveness, scalability, and minimal management. AWS Lambda was an easy choice, as it automatically scales, it has an event-driven hosting setup, and its serverless architecture. Firebase, Heroku, and DigitalOcean were also strong contenders, however, they did not align properly with our goals. In our research for our database for our mobile apps backend, we evaluated the options of Firebase Firestore, MongoDB Atlas, PostgreSQL, and Supabase. The table on the right compares their performance, scalability, ease of use, and security. These are the most important factors that we believe go into creating a strong database. In our final selection for the mobile app database, we landed with Firebase Firestore. We believe the real-time synchronization, its scalability, its user-friendliness, and its security made it an easy choice for us. MongoDB Atlas, PostgreSQL, and Supabase were also strong contenders, but they each had different aspects that were not as applicable to our mobile app's goal.
For the software design flowchart and really the general structure of software that our program is going to be using, there's four main sections. There's motion detection, image processing, and then you can see by the red lines there's alarm management and communication. That's what those indicate. On the figure on the right, there are three different sections. Green on the left indicates our node. Yellow in the middle is for our mobile app, and on the right is blue, which is for our gadget. If you'll look at the node on the left and the gadget on the right, there are two similar architectures, and that is because when you develop an Arduino IDE, there's a setup function that is initially ran, and that's what that first layer is. And then there's a loop function that once everything's set up, such as hardware peripherals and really connecting to the Wi-Fi, that's where we'll live. And inside of loop, we will be monitoring system functionality, looking for stuff like hardware peripherals being raised, like the pacifier sensor, and just stuff like that. For the software state and use case diagrams, on the figure on the left, this is going to be our state diagram. And so inside we have three different states that our node and our gadget are going to be living in. The initial one being a power off where nothing's happened yet. And once power has been turned on, we then move to a setup state where we set up like hardware peripherals and then get all the gadgets and the nodes connected to the router. And then after that, we move to a loop function, which is our monitor system state, where again we will monitor and look for voltage levels being raised for hardware peripherals such as the camera or the pacifier sensor in our system. And for the gadget, it would look something like the switches on our gadget being flipped, and that's where that will be monitored. On the right, you'll see that the mobile app and the gadget actually interact with the user. So the user will have some sort of management console where they have complete control over what they want their system to do and how they want it to act.
Our backend class diagram is found on the left side of the screen. This explains some of the functionalities and interactive requests of our ESP32s. The ESP32 CAM is found on our node device, and the ESP32S3 is found on our gadget device. The image on the right side of the screen refers to our front-end class diagram. This just explains the overall breakdown of our mobile app and how one would navigate through. Here we have a prototype of our mobile app user interface design. This design explains our navigation and other key features such as how we plan on setting up notifications and system control. Now getting into our project's prototyping and testing. Our software testing will encompass all different aspects of our project, including embedded code, communication network, image processing, all up around system, and front-end tests. This will be broken down more in the following slides.
The hardware integration tests include the embedded code for both MCUs to talk to its respective peripherals. We have built breadboards and the PCBs for both the gadget and a node. Our testing includes reading the GPIO pins and verifying successful connections in the serial monitor. In the node, we have tested the passive IR sensor and camera. The passive IR sensor has properly detected motion, and the camera has been able to capture and store images. Our gadget's breadboard and PCB have already been built. We're just waiting on the router connectivity to start working, and then we'll start testing.
All of our communication network tests thus far have been successful. We've been able to properly connect to the gadget as well as the node. We've been able to send messages from the mobile app to the gadget, as well as sending messages from the node to the gadget as well. We're looking now to increase the robustness of our communication network by improving the error handling quality to connectivity issues. The majority of our mobile application UI tests have been successful. However, certain aspects, including some messages being sent to the devices from the homepage, have not been tested. We're looking to test this in the near future as we develop our backend responses.
So for a breakdown of our image processing algorithm and how we are going to be testing it, there are going to be 4 different test scenarios, and in those 4 test scenarios, we're going to be testing each component of how our algorithm would actually work in a real-world scenario. For detection accuracy, we are shooting to at least accurately detect people 60% of the time, given that there's a person in the frame. And so for the first test, we're going to be looking at the static environment detection test, and that's just going to evaluate if a person's able to be detected properly in a very controlled environment. So the person is going to be in the center of the frame, for example. And so for the second test, it's going to be a dynamic environment test. The person's going to be in the center of the frame again, but this time we're going to have some background noise, maybe some movement, some objects behind. And then for the third test, it's going to be low light and shadows. That's going to be testing a little bit more real world scenario where maybe it's nighttime and motion's been detected. How well is our algorithm going to work in that scenario? And then we can improve upon these results and add more data for each certain scenario. And for the last test, it's going to be an obstruction and partial visibility test, meaning that the person's going to be a little bit obstructed and he's not going to be as visible as the other tests. For the system integration test, all up round, AUR, no PCB, the objective for this is just going to be to evaluate the system's overall functionality and identify any potential areas of improvement for our system at a very early stage. A description of this is going to have a target person standing in the center of the frame under ideal lighting and moderate background activity conditions. It's going to work like this. A passive IR sensor, if it detects motion, an image will be captured. Once the image has been captured, the ESP32-CAM uses TensorFlow Lite to perform person detection, and if a person's been detected, an HTTP message is going to go out to the gadget. And so the gadget will then send messages to both the mobile app, and you'll receive a notification on there, and then the gadget will also send a notification out to the nodes to where then the alarm will be sounded. And so success for this looks like seamless operation of all components and accurate notifications for detected threats. And those notifications would look like a mobile app notification and also seeing that the alarms have been sounded.
Now for the project's administrative content.
We decided to cap our budget to encourage better spending. The total cost we estimated is around $500 so far, which is well below what we estimated was needed.
For our milestones, even though the status is incomplete for most of them, we are on track or even a little ahead in a few of those departments. Our hardware is leaving the build stage and entering the integration stage with our software, and our software is maturing to the testing stage as well.
Our software team, Kirby and Jackson, split their work between the front end and back end, respectively. The hardware team, Dylan and I, collaborated on both hardware devices. We split our work between subsystems and peripherals.
All right, a big thank you from our group, and we'll now open it up to questions.